This lesson deals with diode circuit analysis using SPICE. You can find these notes in the ECE302 ebook in Chapter 2, starting on page 20. Since we have the Shockley equation for the diode, why can't we just solve problems using that? Let's try an example and see what the issues are. Let's take a 5-volt battery, 1K resistor, and a real diode, and hook up this circuit. Suppose that I sub S is 2 nanoamps and 8 is equal to 2. These are the default values that are in many of the examples in our textbook. Current in the diode is flowing from anode to cathode, so I'll call it I sub D. Let's go around the loop. The rise in voltage is 5, the drop is I sub D times 1K, and then V sub D. Put the V sub D on this side of the equation, and I'll plug in the Shockley equation for I sub D. So it's I sub S times e to the V sub D over eta V sub T minus 1. I'll use the more precise value of V sub T. So I'm going to compare this to the SPICE program. Now, because there's 5 volts here and something around 0.6 or 0.7 here, current's going to flow in this direction, and we're going to be in the first quadrant, so I could throw the minus 1 away. Multiply this out. 1K times 2 nano, 10 to the 3, 10 to the minus 9 gives me 2 micro, and this product here is 51.73 milli. I got a problem. I've got an exponential here, so I could try to take the natural log of both sides of the equation and get rid of the e, but then I get a natural log on this side. So there is no closed form solution to this equation. And this is called a transcendental equation. The only way to solve it is by iterative guessing. So let's try it. We had around 0.65 in an earlier example. Let's just try that. So put that in here and you get 4.35. And if you put 0.65 in here, you get 0.573. So the left-hand side is bigger than the right-hand side. So it wasn't a very good guess. What I need to do is to make V sub D larger to make this side of the equation go up. Let's try 0.7. Now this becomes 4.3 and this becomes 1.506. Again, this is smaller than this. I need to get this larger, so I'm going to increase V sub D. Let's try 0.8. Gives me 4.2, and now 10.41. Oops, went too far. Need to make this go down. Let's pick a smaller value, say halfway between these two, 0.75, and I get 4.25 for the left side. And I get 3.959 for the right-hand side. I still need to make this a little bit bigger, so let's bump it up a little bit, and I'll add a 5 here in the third place. That makes this 4.245, and now this 4.361. So we did get this larger than this. Now I got to go back and bump it down a little bit. So let's try 3 here instead of a 5. Get 4.247 and 4.195. Need again to raise this up a little bit, so I need to bump it up a little bit. So let's make this maybe 5. I get 4.2465 and 4.236. Now this is smaller than this. I got to bump it up again. So I'll go to 0.7536. I get 4.2464 and 4.244. You can keep going, but that's probably close enough. The voltage across the diode is roughly 0.7536. In engineering notation, that would be 753.6 millivolts. And the current in the diode would be the 5 volts minus the drop across the diode divided by 1K. This type of iterative solution is great for a computer, kind of hard for a person, although some calculators have this capability built in. But this is really what the SPICE program was written for. I'll be using PSpice for the examples in the rest of this course, but a lot of the commands that we're talking about are associated with the original SPICE program. SPICE is an acronym for Simulation Program with Integrated Circuit Emphasis. It costs a lot of money to make an integrated circuit the first time. There are a thing called mask sets. I'm not sure what the current costs are, but I know many years ago it was around $200,000 to make one integrated circuit. Now the material to make an integrated circuit is pretty cheap. It's just silicon, so it's just a few cents to make an IC. So you spend a couple $100,000 to make the first one, the second one's maybe a nickel or a dime, and the third one's a nickel or a dime, and so on. So if you make a mistake, the big expense is up front. The SPICE program was created to try to head off mistakes by simulating the design before you committed to silicon. The diode has the Shockley equation describing it. This is built into the program. In fact, there's even some more variations on the formulas that we talked about. In the program, they needed some way to be able to give the parameters for the diode or for the transistors. They did that through what's called a model line. It begins with a period, and then the word model, and then you give a model name, a type, and then parameters. Whenever I show parentheses here, it's an option. The model name is user specified. We usually give it the part number, but you could call it Fred or Mary or whatever you want to call it. Type is what is it? A diode, we'll put the letter D, and then we'll have different letters for transistors. As I mentioned, the parameters are optional and default values are used. Sometimes this allows us to look at a more idealized component. We had terms in our Shockley equation of eta and I sub s, but when the program was written in the 1970s, they didn't have subscripts and Greek characters. They just had uppercase letters. So they used capital I, capital S for I of S, and just N for eta. The default value of I sub s is 10 femtoamps. That's characteristic of an integrated circuit diode. The diodes we'll be using in lab, it's much, much larger than this, really in nanoamps or picoamps. Value of eta, which we're going to call N, SPICE, is defaulted to 1, and for silicon it's somewhere between 1 and 2. It is a dimensionless quantity. In 201 and 202 we looked at different components in SPICE, and a resistor began with R, a capacitor with C, an inductor with L. A diode begins with the letter D, and you can have up to 7 letters or characters for the remainder of the name. Each diode must be uniquely named. In SPICE, the plus node is first, the minus node is second, so anode will be first, cathode second, and then the model name. You can make diodes identical, or you can make them not identical and see what the effects are. A really good reference book is the book by Rashid. It's out of print, but you can find these on the used market. The SPICE program has a feature for finding the operating point. It'll be very handy for us electronics. Take our circuit and let's make it SPICE compatible, or in this case PSPICE compatible. To do that, you need to label all the nodes in the circuit with numbers or letters, but the ground node must always be called 0. So here I've got 2 nodes, 1 and 2. You can use any numbers, any letters you want. They don't have to be sequential. I typically start with 1 and go from there. Just to review, we have to have a title and a dot end, and then we describe the schematic. In this case, I've got a battery between nodes 1 and 0, plus node first, minus node second, resistor between nodes 1 and 2 with a value of 1K. If I ask for the current in this resistor, it's from the first node to the second node. The diode is from anode to cathode, so from 2 to 0, and we call this D model. So dot model, here's my name, D model. It's a diode, and then I have an I sub s of 2 nano and a value of eta of 2. Then if you ask for the operating point, it's dot OP. I want some more resolution in my output. The default is 4 places. Let's bump that up to 8. So we run the file, and I'll describe that on the next page. For the operating point, get back a table. It gives you all the node voltages in the circuit. Obviously node 1 was 5 volts, but this is the voltage across the diode with 8 significant digits. It also gives the current going in the plus terminal of any voltage source in the circuit. This is our battery, and of course current coming out of it is I sub D, so that would be the negative of that. It also gives the model for the semiconductor, gives the value of I sub D and V sub D, and in this case the model is R equivalent, which we call R sub D. There's only 3 significant places shown here. You can ask for more here, but it won't change this. By iteration, we found that V sub D was 0.7536 volts, and you can see here we've got the exact same result, except there's a few more places. We then calculated I sub D, and you can see we got basically the same answer here. We have a few more places in our hand calculation. You can calculate R sub D, which is eta V sub T over I sub D. It's twice the value of V sub T. I'll plug in the value that we hand calculated, and I get 12.182 ohms, and here you get 12.2. Basically the same answer. One nice feature of the PSPICE program is a thing called DC sweep. It'll allow us to make what's called a curve tracer, and we'll be able to display the VI characteristics of, in this case, a diode. We'll actually build one of these in the 303 lab, but this is a software one. It begins with a period, it's .dc. We then list a sweep variable, a start, an end, and an increment. The sweep variable is the name of any independent voltage or current source, so we can vary any voltage or current source, but just one at a time. Start is the beginning value of the source, end is the last value of the source, and increment is the magnitude of the steps from start to end. Now you can give an increment a negative value, but just ignores it. Let's do an example. Let's take our circuit we're analyzing, and let's plot the VI characteristics of the diode. So again, we got a title, we got our description of the schematic, and now what I'm going to add to this is some comments. If you begin with an asterisk, it ignores that line. Here I'm saying building a curve tracer. I do this so that when I come back to a circuit years later, I know what the file was for. Now what's different here is I'm going to add a line, .dc. I'm going to vary the source, which was called V sub s. I didn't put a value here. It's defaulted to 0 if I don't say anything, but I'm going to vary it from 0 volts to 10 volts in 50 millivolt steps. Now for a graph to look smooth, I need to have at least 200 data points on it. So the reason I pick 50 millivolts is if I take the stop minus the start and divide it by 200, I get 50 millivolts. If you want to run this program at Michigan State University, there is a PSPICE handout on my 302 homepage that describes how to run the SPICE program on the machines in the College of Engineering. If you run the program as described in this handout, you'll get the following graph. Here's a plot of I sub D1 versus the voltage across the diode, which is V2. The default value for the x-axis is the swept variable. That would be my input, and that's not what I want to plot here. I want to plot the voltage across the diode, so you need to change that. That's what the description here on the bottom of the page is. It shows you how to do that in the SPICE program. One other thing I would point out here, that sometimes the line here is hard to see. It's actually set pretty thin. If you click on the line, you can set the width of it. Here I set it equal to 3. I marked the value of the voltage and current at one point, which is roughly what we had hand calculated. In our Shockley equation, the V sub t is obviously a function of temperature, but it also turns out that I sub s is a function of temperature, and in SPICE, this is the equation that's built in. In fact, over time, there are more and more things added to the SPICE program in terms of built-in equations, and we use the dot model line to insert the values into those equations. You can see here there's a ratio of the temperature in your circuit, which you set, I'll show you how to do that in a little bit, relative to the temperature, and that's at 27 degrees C. So when you pick t equal to 27 degrees C, this becomes 1 minus 1, and this becomes 1 raised to a power. So I sub s at 27 degrees C is the value of I of s. E sub g is called a band gap voltage, is defaulted to 1.11, and xti is the temperature coefficient, defaulted to 3. So there's two things that are varying with temperature, V sub t and I sub s. The math there is pretty hairy, so why don't we just measure what happens when we vary temperature. Suppose I start out and set the temperature to minus 23 degrees C. And you can do that with a dot temp line, and then run the program again at 77 degrees C. So I have a change of 100 degrees C. Let's take a look at the results on the next page. Here's the first simulation. I marked a rough value of current that we had at the 27 degree simulation. And you can see here the drop across the diode is actually increased. So as the temperature decreased, the drop across the diode increased for the same current. On the bottom here is the second simulation at 77 degrees C. And for roughly the same current, I've got 0.68 volts. So as the device is heated up, the drop across it begins to decrease. Take a lot of points in between, you'll see that it's linear. Could calculate the change in the voltage across the diode as a function of temperature for the same current. So our first data point minus our second data point, our first data point minus our second data point, and I get 144.5 millivolts for a 100 degrees C change. But it's a negative temperature coefficient of 1.445 millivolts per degree C. The temperature coefficient we just calculated varies with eta and I sub s. So it's somewhere in the neighborhood of minus 2 millivolts per degree C, and most people approximate it that way. And again, what that means is that V sub d decreases by approximately 2 millivolts for every degree C you increase. Even though this changes with different values of eta and I sub s, is very repeatable. In the 303 lab, we'll actually make a thermometer using a silicon diode. You write an equation for that V of t at any temperature is the value of V sub d at room temperature minus 2 milli times the change in temperature from room temperature. So when t is 27 degrees C, you just get the value at 27 degrees C, which is roughly around 0.7 volts or so. Now what about the effects of I sub s by itself? This included I sub s and V sub t. What I could do is change the temperature and see how I sub s changes. I want to put a negative voltage across the diode. I'm going to sweep it now from minus 10 volts to 0. And again, I'll do 200 data points. I started out at 27 degrees C. I purposely typed temperature of 27 here, although the default is 27. Then I ran the program again and kept increasing temperature in small changes until I sub s roughly doubled. When you have a negative voltage across the diode, all you're seeing is I sub s. Let's take a look at the next page to see what the results are. For the first simulation, I see I get minus 2 nanoamps, which is the value of I sub s with a minus 1 multiplied by it. Call this a saturation current, and what they mean by that is that as you change the voltage across it, the current doesn't change. That's what it means to saturate. If you had a sponge and you put water in it, there's a point where you can't put any more water in it, it's just saturated. That's what that means. We use that term in electronics quite a bit, especially with transistors. Here's the second simulation, and again, I ran many simulations till roughly this doubled, and that was really at about minus 4 nanoamps. Let's go back to the previous page at the bottom, draw some conclusions here. From the output on the last page, we can see that I sub s roughly doubled for a 9 degrees C increase in temperature. Now that varies depending on the properties of the semiconductor. Most people approximate that as roughly 10 degrees C. In other words, I sub s roughly doubles every 10 degrees C increase in temperature. In fact, as a student, I actually made a thermometer based on that. You could write an equation for that if you want. 2 raised to the t minus 27 over 10. And multiply that by the value of I sub s at 27 degrees C. So when t is 27 degrees C, we get 2 to the 0, which is 1, which is just the value of I sub s at room temperature. If you were to put 37 here, you'd get 10 over 10, which would be 2 to the 1, so we'd be doubling that, and so on. This is diode circuit analysis using SPICE.